So by now we understand that we need to take help of some computing system in the entire VLSI design process. So for that purpose, we take help of the simulation programs, which are the tools for verifying the IC design at the different stages. So these simulators help us to verify the functionality and the timing behavior of the chip, and we ensure that the chip is behaving chip will potentially behave correctly before we send it to fabrication. In fact, we spend 70% of the total effort in bringing out a chip in the design process only, and rest 30% of the effort comes during or after fabrication. So as I said that today's VLSI circuits comprises of millions of transistors. So you can't use the traditional breadboard method of building and analyzing a circuit in case of practical VLSI circuits. So there's a popular joke over here that you fabricate an IC and then at the end of the testing phase you detect that the design is faulty. What will you do? You spent so much effort in designing the circuit, analyzing it, you fabricated it, and after fabrication you are testing it. At the final phase of the testing you detect that your design is faulty. So human errors leads to far-reaching problems when it comes to VLSI design process. Obviously mistakes helps us to learn, but when it comes to a design comprising of millions of transistors, should we again repeat designing the circuit consisting of millions of transistors with using the pencil and paper approach? No. So the circuit has to be spiced before it is cooked, and spiced well and many times before each stage of the design and after each design step. So
what is spice so that you get the real joke?
Spice can mean a masala, spice can mean a simulation program with integrated circuit emphasis. So more you do simulation, more you do analyze the circuit, your circuit is going to be tastier, right? And this is called the analyzing the circuit. And analysis tests the quality of synthesis. So what is SPICE? It is basically simulation program with integrated circuit emphasis. So SPICE is essentially a simulation program and it is used as an analysis tool. Two popular hardware descriptions are used at the immediate top level above SPICE to, it can span from algorithmic description of the system down to the gate level. So two popular HDLs are used, one is the Verilog and the other one is the VHDL. So over here in this course we shall be learning Verilog as a hardware description language. You can also, after the course is over, you can also go on learning VHDL or system Verilog or system C, blue spec, system Verilog and so on. So using Verilog one can design, simulate and synthesize. So as I said that one of the essential features of this hardware description language is to model the concurrency of the hardware modules. And apart from that, you should also check check and report of timing errors or not. So using Verilog, you can do all this timing and clocking, checking and all that. You can design asynchronous as well as synchronous sequential circuits with it. I hope by now you know what you really mean by an asynchronous sequential circuit, what you really mean by a synchronous sequential circuit. And logic operation and timing behavior can be simulated. To see the hardware design flow, we start with hierarchically splitting the system into subsystems, sub-subsystems and so on, and then we code for each of these modules, compile the modules, and then simulate and verify the designs and find whether the design contains any bugs or not. By bugs, I mean not just the syntactic bugs, it can mean a fundamental design flaw also. So that is evident from this by simulating the circuit. After the simulation, you synthesize the circuit using some synthesis tool, and then perform a placing of the components and routing and establishing the interconnection to the components, and finally do the timing verification to ensure that the chip being designed meets its requirement specifications or not. So this modeling and simulation part, we call it the front end design, and the synthesis and place and route and timing verification, we popularly call it the back end design. To look at a simple Verilog code, because we are learning Verilog, let's first start by seeing a simple Verilog code which basically models a 2-to-1 multiplexer. So Verilog code in essence comprises of a set of statements embedded between a module and an end module declaration. So after module, you define what module you are going to model and define the set of interfaces it has within the parenthesis. Next, you define what are the input and what are the output interfaces it has. And then comes the body, in which you describe what is there inside the module. So over here we are basically giving a behavioral description of the module, which means we are basically describing the 2-to-1 multiplexer from a functional perspective. So the module is the basic building block in VHDL, in Verilog, sorry. The module is created by declaration, and you can't declare a module within another module, it cannot be nested. However, within a module you can use the instances of modules which you have defined earlier. The module is basically the black box for the particular circuit you are developing. So the interfaces to the black box are defined by its ports, and when a circuit description contains multiple modules, all these modules, they run concurrently. So over here we see that we have defined an adder module, and then we are instantiating the adder module within another module which we called adder_tree, and we have created, we have called two instances of the module adder. So we are not really defining a module within a module, but we are basically instantiating a module within another module. So the module basically provides us a template from which we can create actual objects. So in one sense, you can establish a correlation between a module in Verilog and a class in C++, right? So with a class, you can define its set of data members and the function members, and when you really want to use it in some program, you create objects of the class. In the similar way, you can define a module and instantiate the module at different places of requirement in your Verilog model. So when a module is invoked, Verilog creates an unique object from the template. Each object has got its own name, variables, parameters, and input-output interfaces. Now, how we can really define the interfaces of the modules? The simplest way is you specify the interfaces of the instance of the module in some ordered fashion, in which the order of the ports of the instance is same as the order of the analogous interface in the mother module.